So welcome back, everybody. This is the program for this week. I wanted to also remind you quickly of some of the practicalities which we discussed last week. Also, I see now that there are more than 30 people who have compiled that specific form on potential partners for the lab and the projects and the exercises. So I will actually try to compile a suggestion by the end of today. Now, if we just go quickly back to what we have on the official website, as we mentioned last time, we have a schedule here, and when you can always subscribe to these activities. And this is where you will find the lecture notes, exercises, the links to everything which you need. As you probably have seen, you're also getting an email, the same type of announcements. If we now just go back to the fall 2024, you will find the same type of announcements under messages, and you will also find the same stuff in Canvas, in addition to the email which you get. So hopefully everybody got the message about us being here. Then, coming to the program for the day today, we are going to have a quick repetition from last week. And then after that repetition, we are going to look a little bit about the mathematics of linear regression, which is a kind of low-level machine learning method, as we discussed last time. I wanted also to point to you the kind of material which is relevant for the exercises this week. So we have a weekly set of exercises which give you one additional point for the final score, and each week. And these exercises will be discussed during the lab sessions. We want them to have a more kind of active learning sessions. And in the beginning of these slides, you will find material which is relevant for the solution of the exercises. And there are some technicalities in particular with exercise 1. Now, where do I find all this material? There is obviously a link here. If you go to you can either go to the doc folder here, or you can just go to the Jupyter book, and then you scroll down along the page here, and you will find the week 35 weekly material. So that's the material you were watching in that Jupyter notebook. And you will also find the exercises for week 35. Now, I just wanted to guide a little bit the eye, because the analytical exercises deal with derivative of vectors, scalars, multidimensional scalars, because our objects now depend on many parameters. And for some of you, this may be something which you've seen 2 to 3 years ago, when you took a course on calculus and multidimensional variables. So the material which you find in the beginning of the material for this week actually deals with some of these technicalities. So take a look at that when you're going to solve exercise number 1. Then there is also material for solving exercises 2 and 3. And many of you last week, you actually almost ended solving exercise number 2. So exercise number 3 is something which we'll also discuss a little bit at the lab session. So in the beginning of the lab sessions, we will try to guide your solution of the exercises in the best possible way. And then in the lectures today, we are going to look at the mathematical interpretations. So this course tries to strike a balance, as we said, between the mathematics of many of these machine learning methods, applications of the methods, programming, obviously, and then analysis of specific data sets which you may be interested in, or which we are suggesting for you. And when it comes to some of the exercises, there is actually a pretty good book which is fully available as a PDF online. And that's the book by Faisal and Ong and Dijsenroth, which is just called The Mathematics of Machine Learning. And if you go into chapter 5, if you think you're a little bit rusty about the mathematics of vectors and matrices, there's actually in chapter 5, there is a pretty good reminder. And that book is typically at the level of the second or third year of a bachelor study. So it should be hopefully a text which can be of help to many of you, just to remember various definitions which you probably have seen. But normally what we saw from 2 to 3 years ago is not necessarily something which we remember immediately. Now, the material which you see here is also something which we will discuss again during the exercises. But last week, we actually calculated the derivatives of these quantities, or rather, we set up the final expression for linear regression. So let me quickly point to you to some of the material which is relevant for the solution of the first exercise. And this material is actually taken from that textbook which I mentioned. Any questions, guys? Okay, so the equation which we looked at was actually the equation for the mean squared error, which then leads to, when we take the derivatives, we can actually rewrite it term by term. We assume that we could make a polynomial approximation, where now the parameters of a polynomial are given that by these unknown quantities beta j. So this is what we did both during the exercise session and in the lecture last week. And you can actually write it out like this, or since you have p elements of this beta, you could set it up as a vector. You can set it up as a transpose or just the column vector. And in order to find this expression here, which is the one we typically use for linear regression, we actually ended up with the optimal parameter, which is given by the inversion of a matrix, where this matrix X is what we call the design matrix. And you're going to practice using this one in exercises 2 and 3. So you can actually, if you want, you can just stay with these equations here, or you can make it in a more, write everything in a more compact way, like a matrix inversion problem. And that's typically the way you would do now your first machine learning task, where you learn the optimal parameter beta by inverting a matrix. So you have a well-determined mathematical algorithm, which is then set up to solve the problem, okay? And then there are things which can be useful to remember. So take a look at these things till the exercise sessions tomorrow or on Wednesday. We are going to repeat this during the session as well. But try to take a look at it before we meet at the sessions. And if you now look at the quantity y here, which is a function of some f of x, we know that this y is now a vector which has m elements. And then this x could be a vector which has n elements. And that means that you can define the derivatives of these various components y in terms of what's called the Jacobian matrix. So when you did multivariable analysis, you probably saw something like this. Does this ring a bell? Okay, I can see many heads nodding here. If not, I mean, it's okay just to revisit it. And that textbook, which I mentioned in chapter 5, has some of the basic mathematics about this setup of a derivative. Because now you're taking the partial derivatives with respect to different variables. And clearly, you can organize this matrix as you want. So in this specific case, I have, as you can see here, I have n rows and m columns, but you can obviously change that one. And then when you do the derivatives, these exercises, or these examples here, are actually pretty useful. So take a look at these examples. And we are going to discuss them in more detail tomorrow. I will not do that in the lecture here today, okay? Because this becomes more like a technicality for the solution of exercises, but you have essentially the kind of recipe. And one way to actually do this is to write out things component by component. And the easiest way, if you're a little bit in doubt, if this doesn't ring a bell immediately, you can always write this down. If you think of a matrix vector multiplication, if you multiply a matrix with a vector, this is obviously a vector, right? And then when you spell it out like this, you can now calculate the derivative with respect to one of these components K. And this derivative, which you see here, is nothing what you have in this matrix. So this Jacobian matrix is just you organizing everything in terms of a matrix. Now, there's a reason why we do this. We find it, from a pedagogical point of view, actually quite important to actually start wrapping your brain around this way of writing things. Essentially because when you're going to write a code for a neural network, you're going to have series of such matrix multiplications, matrix vector multiplications involving the derivatives of the different constants. So that means that having a kind of intuition about the way we organize these quantities and what we should get is very important for a properly working algorithm. So a neural network is nothing but a set of matrix vector multiplication involving derivatives. So if you want to look at the mathematics of it, this is what you have at the heart of the training with a neural network. And when you have derivatives of vectors and matrices, then these kind of exercises and this kind of machinery gives you a compact way of expressing it. But then you have to always keep track of the right dimensionalities, because that can quickly lead to wrong results if you don't do that. So in a way, it's not an exciting topic. It's an important bookkeeping topic. So that's the main motivation behind it. So one of the examples, and we will come back to this during the lab sessions. So you could typically write the matrix vector multiplication in terms of the components. And when you take the derivative then, you will then find that the derivative with respect to a given component is simply given by the matrix element. And you're assuming now that the matrix A does not depend on X. So this is important actually, because when we go back to the expressions for linear regression, we have made an assumption that this X does not depend on the unknown parameters beta. So you have to make some specific assumptions in order to use this specific expression. In other cases, you may have a dependence on the unknown parameter X, and then clearly you have to pay attention. And there are several examples here. So just take a look at them, because we want you to derive the equation for linear regression as we did, because last week we just gave you the final expression. Now we want you to derive it by taking derivatives of matrices and vectors. Okay? So you can actually follow, and you can see there are many examples here. Keep in mind that the mean square error is a scalar. It's just a number. So in that case, if you think of the mean squared error, it involves something which looks like this. So this example, which you see here, is an example of where you set up a scalar in terms of matrices and vectors. And now we take the derivative of a scalar with respect to vector components. And this is essentially what we did. If we go up a little bit and we look at this expression here, here we have detailed the expression. So the mean squared error is this function C. And then we are simply calculating the derivative with respect to one of these quantities. So this is just another example of you spelling out the derivative of a scalar. In other cases, it could be a matrix or it could be a vector. So I take the liberty of giving small, not exactly homeworks, but reading suggestions. And you will find these reading suggestions in the beginning of the lecture notes as well. So, and hopefully this can help you in solving the exercises and the projects. Now, you will find many more examples, and you will also find an example which is close to what you do for the calculation of the mean squared error. But what I want to do now is to actually jump to the material which is relevant. So some of these things are actually code examples. If you feel a little bit rusty about getting started with the Python programming. So one thing which we always tell people, feel free to use these codes as you want. But when you use them in a project, you should always cite what you have used. This goes also back to the way we would use ChatGPT or some of these other artificial intelligence softwares, which are so handy. So you should always cite, if you borrow something from a source, always cite the source. But feel free to use these codes as examples. And we are going to discuss some of them in the lab sessions as well. So this was a material typically which you will find every week. We may not be able to cover everything. As you can see, there's a lot of stuff. But we leave much of this as material which can be used as background material. And what I wanted to bring up now is the material for the lecture here. And I'm going to slow down often the pace by just using my whiteboard. And I wanted to discuss some of the mathematical interpretations of linear regression. So when I'm standing here, can you in the back hear me? No problems? Oh, good. Because I tend to move, so that's simply because my brain has always been coupled to my legs. That's where the main thinking is done actually. Okay, so let's switch to the whiteboard and take a look at some of these technicalities and try to get an understanding of what linear regression actually means. Now, there's a meaning behind this. And the meaning has to do with the fact that we want to introduce better methods than linear regression. So one of the sources of errors, which you saw in linear regression, was actually that matrix, which we want to invert, can be singular. And that clearly creates problems. When you have a polynomial approximation, like the examples we went through last week, this is normally not a problem. But if we have dependencies between the different columns, then we can easily have a matrix which leads to a determinant which is 0 or eigenvalues which are 0. These are just equivalent statements, okay? So there are tricks which you can use to avoid that. The cheapest trick, which actually people introduced, is just by adding a small number along the diagonal. So if you go back to many numerical codes back from the 60s and 70s, they would often introduce a parameter which they call 0, which was something like 10 to the minus 8 or 10 to the minus 10. And then you would add 0 along the diagonal, and then you could invert the matrix. That's cheating. However, yeah. 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 So could you say again, because I have this kind of. Yeah. 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 So if you think of a matrix which is orthogonal, that means that every column defines an orthogonal vector. So if you do a polynomial approximation, then each column represents a degree of the polynomial. So you could say one column represents x, the other one x squared. If you take the norm of these two columns, that is 0. So when you construct a polynomial approximations, you will normally by definition, or you not necessarily, but you will normally not have column elements which have a dependence from each other. So with dependence, I mean that there is a constant times another column, so that the two columns are essentially the same except by a constant. Yeah, that wouldn't spread, exactly. So the fact that you have a set of orthogonal polynomials is normally something which makes that object invertible. But you always have to be careful, because you can have dependencies which can sneak in, or you make an error or whatever. If you have data sets like the cancer data which we discussed last week, then you could have one column which represents the area of the tumor, and the other column which could be the radius squared, for instance. So obviously these two quantities would be related to each other by just a constant. Sometimes you have the perimeter as a kind of how to say parameter to define a tumor, and the perimeter is directly proportional with the radius. You just have 2 pi times the radius. So that would be an example of columns which could lead to dependencies, and then problems with inverting that matrix. So the general situation is that you can encounter matrices where you have dependencies between the columns. So that means one column is just proportional to the other one multiplied by some constants. Okay, so what we are going to do now is just to switch to the whiteboard here. And we are going to take a closer look at the mathematics of these methods here. So what we have defined is something which we call the mean squared error. And we have defined that one to be a function of these unknown parameters beta. So in our case, this function, the loss function or the cost function, is given by the mean squared error, which is now a expectation value over the sum of observations which we have of I equals 0, of n minus 1, and then I have y of I. And we made a model last week where we assumed that we could parameterize the model in terms of a polynomial approximation. So that's just a model which we cooked up. You can use other types of ways of representing your model. So in this specific case, what we had was a sum over all these unknown parameters. And then we have a polynomial of degree beta j multiplied with x of I to the power of j. And this is squared. Now, then, when we took the derivative, so what this actually means is that one of these model outputs which we have is simply now given by this polynomial of a certain degree. And then we have a beta j of x of I to the power of j. And so this is our model. And beta j's are the unknown parameters. And what we found last week, which you're also going to derive in this exercise number 1, is that this optimal parameters beta, so that's the optimal one, is given by this matrix X, which we call the design matrix, times the, so we have this times this. This is a design matrix inverse. So this is a quantity we have to invert, multiplied with the matrix transpose times y. So this is what we set up last week. And many of you did actually start to program that for polynomials of different approximations. And we will continue with that, with the exercises, same exercises this week, in exercises 2 and 3. And in exercise 1, you're going to find this expression. Okay, so the question now is, what does this mean for us? So let's now take a simple example, so, which I'm also going to use to remind you a little bit about linear algebra. So suppose now that X is an orthogonal matrix. Actually, this is a pretty boring case. So X orthogonal. Which means that X transpose times X And this is, remember now that this quantity here, X transpose times X, these were now set up. This becomes a matrix of dimensionality P times P. So if I do that, if X is an orthogonal matrix, these are normally square matrices, then we know that this is equal to the identity matrix, which I'm going to write like this. So that means that you just have ones along the diagonal and zeros else. Does that ring a bell? That's an orthogonal matrix. This is actually a pretty boring case. So this is a square matrix, because if it is an orthogonal matrix, what we will have then is obviously that the parameter which we have y, which is given by this matrix times beta, the optimal beta is actually x times x transpose times x of x transpose times y. So if x is an orthogonal matrix, what is our model like? If you look at that expression, it's equal to y, right? Correct. So this means that y, if I do that, this is just the identity matrix. And then I have the identity matrix multiplied with identity matrix. So that's the identity matrix squared. So this is simply y. That's actually a useful test of what is going on. Now, what does actually this type of model which we have made, what does that mean mathematically? So one way to look at that is to look closer at what we have here. So what does that mean mathematically? What you could do then is to define a matrix A, which is given by this design matrix. So this should be -1 here, sorry. I forgot that one, of x -1 of x transpose. So if you look at that matrix has a special property, and you can actually prove that immediately. So this matrix has a property that if I take a squared, it's actually equal to itself. And you can see that if you multiply that matrix with itself. And simply because if you are now assuming that that matrix, this matrix does not need to be orthogonal. So this assumption which we are doing now does not need to require that the matrix X is orthogonal. But if you multiply them out, they're going to act like that. Now, do you remember what you would call this type of matrices? So in the literature, they have a specific name in linear algebra. Anyone who remembers that? Projection matrix. And these matrices are normally called idempotent. So this is actually a matrix which projects out some specific components. So when you act, so this is in the literature, this is a projection matrix. So what I'm doing then is that I'm writing y tilde equal to this matrix A times y. So what I'm doing is actually to project out components of y, which are defined by the column vectors of the design matrix X. So normally, y is not equal to y tilde, because if it was, we would have a perfect model, right? But we are normally guessing. So the kind of approximation we make now means that we are making a projection of the full vector y to a new space, and this is defined by the column vectors of X. That is one interpretation. Now, later, we are going to introduce a very important theorem in linear algebra, which is called the singular value decomposition. So have you met that one in your course in linear algebra? This is, if you ask me, the most beautiful theorem in linear algebra. And you can essentially do everything with a matrix with that. So this interpretation or this expression which we have here means that y tilde can be viewed as a projection sorry for that, of y, the original one, in terms of the column vectors, of the matrix X. And just a quick reminder of what we did is that this matrix X with a polynomial approximation was now given by these ones, which we had here, which defines the intercept. And then we had x0 to the power of 1, x0 to the power of 2, x0 to the power of p minus 1. Then we had x1, etc., down to xn minus 1. And this goes all the way up to xn minus 1 to the power of p minus 1. So this is this specific model we have made. It could also be represented by other types of functions. You could think of having a sine function, a cosine function, or elements of a Fourier series, or whatever you are interested in, which you think is ideally suited for the data you are studying. Now, we in the first exercises, we just deal with a polynomial approximation because this is something which everybody hopefully is familiar with. Okay, any questions? So one of the things which we are going to do now is to introduce something which is called a singular value decomposition. So I will just state the theorem. I'm not going to derive the theorem. Some of you may have seen that when you took linear algebra. So how many of you have seen the singular value decomposition of a matrix? So let's see here. Yeah, it depends a little bit on who teaches linear algebra. So if I'd been teaching it, you would have seen it. But that's because we are now going to make a different interpretation of linear regression. The reason why we do that is that the singular value decomposition is also the method you will use to calculate the inverse of this matrix. And that leads normally to more stable results. So that's something which in Python you will see called the pseudo-inverse, or the Monroe-Penrose inverse of a matrix. So let's now just go remind you of the singular value decomposition, because that is also going to give us some deeper understanding of what linear regression actually means. So there's one intermediate thing I want to give you guys. So we've seen that the derivative of the mean squared error, so dc d beta, we require that one to be 0. And we found that that is equal to minus 2n. And we have x transpose times y minus x times b. Now, one thing you will also see in exercise 1 this week. So in exercise 1, there is another quantity which plays an important role in all of machine learning. If I take the second derivative, and this is going to be a matrix, so I have a transpose here, and you're going to find this quantity in the exercise 1 when you take derivatives. This is actually given by 2 over n and x transpose times x. This applies to the mean squared error. If you have another function you're optimizing, you will not get this, okay? So last week I told you that the linear regression with the mean squared error is a kind of entry point when we start looking at machine learning. And one of the reasons for that is that we have nice analytical expressions for many quantities. Now, the second derivative here plays an important role in statistical data analysis. And you will see this again and again, because we are going to make a Taylor expansion later around the optimal parameter beta. And we're going to use that Taylor expansion to set up Newton's method. Does everybody remember Newton's method? Okay, not everybody. We're going to use that one. That's going to be central in the optimization part. So one of the things we will show now is that this matrix, which has a name in the literature, or this quantity here, it's called the Hessian. In the optimization part, this is the object you will hate to calculate, and which we will approximate with constants. And things like a learning rate in the optimization part. Is any one of you familiar with that concept, learning rate? Somebody have heard of that? Yeah. This is connected with the fact that you don't want to connect this quantity. You don't want to calculate that quantity when you're doing the optimization. Now, one thing we will show now is that this matrix leads to a convex problem when you do mean squared error. So that means that when we take the first derivative, we actually have a minimum. So we are dealing with a convex optimization problem. This is what we do here. I mentioned last week that optimization is at the heart of all of machine learning. So what we will show now with a singular value decomposition is that this matrix has only positive eigenvalues. If it has only positive eigenvalues, it means that all the variables you are trying to optimize, they correspond to a minimization problem. So that's a useful information. Now, this object enters the optimization part. And you see quickly that this matrix can be big. If you have 1,000 parameters, it's 1,000 times 1,000 matrix. There are many ways to circumvent that one, and we are going to meet that in the optimization part. There is a famous algorithm called ADAM. Has anyone of you heard of that? In the optimization part. That article was presented in 2014. It says it stands for adaptive method with the momentum. And it was introduced in 2014, and it has now more than 200,000 citations. That tells you how important the optimization part is in machine learning. And so you should just frame in this object, paste it on you close to your bed. So before you go to sleep every night, you watch it and say, I'm not going to calculate you. So in the optimization part, we try to circumvent the calculation of the second derivative. That's very important because you end up with many parameters, and this is something which becomes an intractable path. So just think of a Taylor expansion around the minimum for the cost function, and then you know that, and if you retain terms to the second order, you have second derivatives, and that leads to Newton's method. And the Newton's method, which is the one we try to implement for optimizing the problem, we would like to avoid calculating the second derivative. So I'm just anticipating one of the central parts in machine learning, the optimization part, okay? But now we just stay with the mathematics of the method and try to take a look at what this matrix, how it can be interpreted, and how we can interpret the standard ordinary least squares. So this is a method we've been dealing with in terms of a singular value decomposition. So we need to remind ourselves about the singular value decomposition. So what is the SVD? So SVD, that's a singular value decomposition of a matrix. This is an algorithm which plays a central role in many machine learning methods. And it's also used in something which is called principal component analysis, when we try to reduce the dimensionality of the problem. So the singular value, so I'm just going to repeat what the theorem says. I'm not going to derive it. We are just going to, in this course, we will often use results from linear algebra or from optimization theory. We will state the theorems, but we will apply them. So we're not going to spend time on deriving them, because that would easily be 4 hours of lectures, okay? So I'm just taking the liberty of just stating it. So what it means is that I can decompose a given matrix, decompose matrix X, the design matrix which we have, as follows. So there is a matrix U multiplied with a matrix sigma multiplied with a transpose of another matrix. Now X, as we said, doesn't need to be a square matrix. We assume that it's a real matrix of dimension n times p. Now U is a unitary matrix which has dimension n times n, and this matrix is unitary, so that means that U times its transpose is equal to U transpose times U equal to 1. The identity matrix. Yeah. Orthogonals. Yeah, sorry, orthogonal. Thanks. It's an orthogonal matrix. So we are essentially dealing with real entries. So if you have the complex entries, this should be a unitary matrix. So I'm so used to quantum mechanics where we only deal with unitary matrices. Okay. And V is a similar matrix, but it has another dimensionality, P times P. And it goes like V transpose, same, it's an orthogonal matrix. So this is V transpose times V is equal to the identity matrix. And what this means is that every column of these matrices forms an orthogonal vector. Okay, so everybody gotten it? You see some people still writing. You will actually find these whiteboard notes online afterwards. So if you don't get time to write down everything, you can always look them up. So what it means is that every matrix U here can be written in a more compact form, like a vector U0. So these are vectors up to a vector U of n and minus 1. And each one of these vectors, like U of I transpose times U of j, is equal to delta ij. So these are orthogonal. And the same with V. If we write every matrix in terms of a column vector, so every entry here is a vector. So I have a V0, V1, up to Vp minus 1. And again here, what I have is that V of I transpose times V of j is equal to delta ij. The matrix sigma is a matrix which has dimensionality n times p, and it contains what are called the singular values. So there's a sigma 0, sigma 1, up to the last non-zero quantity. And then the remaining quantities here are 0. So the matrix has dimensionality n times p, but it has a set of values along the diagonals which do not need to be non-zero. So we call these quantities the singular values. And these quantities are normally organized so that sigma 0 is larger than sigma 1, larger than sigma 2, and then up to sigma p minus 1, which is larger than 0. So before we take a break, I just wanted to give you an example of such a matrix. So this is a singular value decomposition, which simply says that you can take any matrix and decompose it like this, even if the matrix has 0 eigenvalues, which is the same as it cannot be inverted, and that it has a determinant equal to 0. So you can always singular value decompose a matrix. And that's why this theorem is so powerful. So let me also give you an example, and then we take a small break. So an example could be a 3 by 2 matrix 3 by 2 here. So we have sigma, which now could be equal to 2, 0, 0, 1, and then 0, 0. That's just an example of such a matrix for this sigma here. And you see these values are larger than 0, and then you can have zeros. So in case your matrix cannot be inverted, or it has 0 eigenvalues, you can perform a singular value decomposition, but you will find some zeros. So you cannot escape the fact that it cannot be inverted, or that it has 0 eigenvalues. But you can always decompose it. And the power of this method relies in the fact that you can decompose it. And this is what we will use now after the break to show that the mean squared error problem is a convex optimization problem. And this is a useful thing to know because we know what kind of optimization problem we are dealing with. Okay? I know this is a little bit more disconnected from what we do practically in the lab sessions, but I think it's useful to have this kind of background understanding of what the methods mean. Because in the next lecture, after we've done the mathematical interpretations, we are going to introduce a method which will always be stable and which is called ridge regression. But that introduces an additional tuning parameter in the optimization. So many of you will be deeply disappointed when you come to the actual implementation of machine learning methods, because we are going to tune many additional parameters in order to optimize a function. And some people are left with feeling, hey, well, what I'm doing is just to tune parameters. Where's the meaning of what I'm doing? So the thing is that you should then get an understanding of what these parameters mean, because that is when you can use them with some confidence. So the whole thing with this course is actually to get the practical understanding on how you implement them, write your own codes, but at the same time, understand the limits. So everything we do, in order to be able to use it properly, we have to know the pros and the cons of a given method. It's only then when we can develop new things. Okay? So I hope you can bear with me when I dive more into some of these mathematical interpretations. Hopefully that gives you this kind of broader background. I went a little bit over time deliberately. I will try not to do that. So I will try to give back some minutes of your life. Now I stole 4 minutes. So let's try to begin at 11:20. Is that okay? Then we do 15 minutes. Feel free to ask questions, stretch legs or whatever. Okay, welcome back again. So the aim now is to go through some of the mathematics, and at the end, we are going to introduce a method which we will also play around with in project number 1, which is called ridge regression. And later we will also encounter something which is called lasso regression. And I will try to explain to you what that actually means mathematically. But let's take a look at the singular value decomposition and discuss a little bit ordinary least squares. Ordinary least squares is when we just take the mean squared error and take the derivative of that one with respect to the unknown parameters beta. So if you now just do some playing around with these equations here, you can see now that if you multiply sigma t with sigma, this is something which looks like 4, 0, 0, 1. So one of the important elements in the analysis, which is coming now, deals with this playing around with the matrices of different dimensions. And when we do sigma transpose times sigma, we get a matrix which contains only the diagonal singular values and 0 else. If I, on the other hand, take the matrix sigma and multiply with a transpose, then I'm going to get a 3 by 3 matrix, which you can see now by taking that matrix up there, which is a 3 by 2. If I take a 3 by 2 times its transpose, it's a 3 by 2 times a 2 by 3 matrix, and that ends up being a 3 by 3 matrix. So this becomes equal to the same element which we had before, but now we have zeros, 0, 1, 0, 0, 0, 0. Now, I bring this up because it's useful to keep this example in mind when I'm going to show the mathematical meaning of the ordinary least squares using a singular value decomposition. Now, before we do that, I'm going to do a small intermezzo here. So if you look at the matrix which we have, this X transpose times X, which is also the second derivative of the mean squared error. It's proportional to that one. We can write this out now in terms of the singular value decomposition. So that has a matrix V times sigma T times U of T times U times sigma times V of T. So what I'm doing now is simply to perform a matrix multiplication of the singular valued decomposition. Now, we know that in this specific case, this is just the identity matrix, but this has dimensionality n times n. Now, this guy here has dimensionality n times p. This has dimensionality p times p. This guy here goes like p times n. And this one has dimensionality p times p. And these final ones here have dimensionality p times p. So one thing we know that this one just gives us the identity matrix, but when we now perform these multiplications, what this means is that we are just left with V of sigma transpose times sigma times V transpose. Okay? So if you look back, we know that this sigma transpose times sigma is just a P times P matrix, in this case 2 by 2, and it contains only the singular value, but these are squared. So this would be, if we now have two singular values, this would be sigma 0 squared and sigma 1 squared. If we wish just to keep this labeling without putting in an explicit value. Now, this is interesting. Why is it interesting? Now, if I multiply X transpose times X and multiply that with V here, that is given by V times sigma transpose times sigma times V transpose times V. And this is just the identity matrix of dimensionality P times P. Now it becomes interesting because what we have here, if I now pick one of the orthogonal vectors. So remember now that this matrix V contains, if we go back here a little bit, it contains a series of orthogonal vectors. Okay, so when I'm now multiplying with this V here, this specific quantity you see here, it means I can take vector by vector. And if I pick one vector, what I'm going to get then is X transposed times X times a vector V of I. And that is obviously the vector V of I times sigma I squared. What do we call that problem? Which you have here. We actually have the solution. If you have the vectors V, we have the solution. So what kind of, in linear algebra, what would you call this? You have a vector times a matrix is equal to a vector times a value. Eigenvalue problem, right? So what does this mean? It means that the eigenvalues of the matrix X transpose times X are given by the singular values, which are all larger than 0. Now, we also said that this matrix here, this one, is proportional to the second derivative of the cost function we had, to the mean squared error. This means that if all the eigenvalues which correspond to a given parameter are positive, this is a convex optimization problem. Because the second derivative, if that is positive at the minimum, then we have a convex function to optimize, which is the same as a minimization problem. Okay? So what we have shown here is that the mean squared error corresponds to a convex optimization problem, which we simply call a minimization problem. We have shown, because all, by definition from the singular value decomposition, all these sigma i's are positive numbers. So we call this matrix X transpose times X a positive definite matrix. Does that ring a bell? So a positive definite matrix has all eigenvalues positive. And this is proof for the demonstration that the minimization of the mean squared error leads to a convex optimization problem. So the consequence here is that this is a convex optimization problem. So let's just write it like that. Convex optimization or minimization. And I'm going to put an arrow here up to the quantity here, because this quantity is the second derivative. Second derivative, deriv of the cost function, or the mean squared error. Now, but there's a little bit more to the picture than meets the eye here, because we are going to look at how we can interpret that in terms of the final solution using the singular value decomposition. So now comes another thing. Is this okay? So I just want to give you this detail because it has an importance for us later, in the sense that if you look at the function we are optimizing, it's very seldom we know that that function leads to a minimization problem and that there is a global minimum. That is what we might call the pleasant cases in machine learning. When you are optimizing a neural network, you can have millions of parameters and you don't know whether you have an optimization problem which leads to minimization and maximization, or whether the quantities you find correspond to a global minimum or a local minimum, or even worse, a saddle point. So the kind of situation you will often encounter if you think of a function of some parameters, f or beta, then you have beta here, you could get something which looks like this, something like that, and something like this. So what you want is the best representation, the one which minimizes the function. So clearly you want to be here, right? But if you start your favorite optimization method at a point like this one, you may get trapped here after some iterations because you're going to use something which looks like Newton's method. That's the standard method and variations of it, which is used to find the optimal values. So it sounds very primitive, but when you do calculations, there is always a balance you have to strike between the number of CPU cycles you want to invest and the time you're willing to wait, and the precision of the data you want to have. So this is a kind of balance you guys have to strike when you're going to run the projects. So every time you run a calculation, you may get slightly different meaning in a multidimensional function. So if you go back to many of these large language models, they have trillions of parameters. Trillions. That means 10 to the 12 or more. So this function which you have here is a one-dimensional function. So according to my wife and my daughter, I'm a kind of one-dimensional guy. So as soon as I move beyond 2 dimensions or 3 dimensions, I'm in deep problems. Anyway, this is the kind of plots I will try to make. Going beyond that is beyond my capabilities. Joke. But anyway, there's another point which is a mean case to land in. What happens if you are here? Because here as well, your d of f of d of beta is equal to 0. What do we call such a point? Anyone who remembers that? Saddle point. That's a saddle point. And that is also one of these cases where you get a derivative which is 0, and you may say, hey, I found a minimum, maximum. But you would actually be stuck in a point then, because your algorithm would then stop, because you have a requirement which says that, okay, now I have reached a minimum, my derivative is 0, and now I stop calculating. That's a pretty common test you would have in these optimization algorithms. So I'm just presenting this one because we will bring it back again when we start looking at the optimization part. With linear regression, as of now, we have gentle analytical equations. And in a certain sense, we don't need to think about these kind of problems, not yet. But we have to keep them in the back of our mind, because this is something which we will have to deal with for any machine learning algorithm. We're going to have a multi-dimensional function we want to optimize. So it's not meant to discourage you, because we are going to run calculations, but we have to keep this in mind. Okay, so the step which I wanted to say a little bit about is now the understanding of the final expression. So what we had is y tilde, which is equal to our model x times beta, which then is the same as x times x transpose times x inverse times x transpose times y. No, sorry, and this is multiplied with, sorry, yeah. No, this is x times beta. Yeah, exactly. Okay, so this is what we have. So what does it mean in terms of a singular value decomposition? So before the break, we looked at this as a matrix, which we called A. And what we said then is that we could make a projection of y defined by the space of the vectors of the design matrix. When we do the singular value decomposition, we can actually get a more compact mathematical expression in terms of the singular value vectors. So let's see how that happens. So with the SVD. So what happens then is that I can rewrite this matrix X in terms of U times sigma times V of t. And then what I have is that my result then, which I have written down, my y tilde, becomes then equal to, if you go back to the previous slide, so what I'm doing now, I'm simply inserting the expression for x in terms of a singular value decomposition. So I would get then u times sigma times v transpose, and then I have this quantity which I have to invert, which we found before the break, which is v of t of -1. And this is a p times p matrix. And then I have this one multiplied with v times sigma t transpose times u of t multiplied with y. So this sounds like a extreme complication, okay? So why do I do it like this? Because we're going to get a simple expression. And that simple expression is going to be very, very important for us in order to understand the next method, which is called ridge regression. So now I'm going to put a subscript here where I call this OLS. OLS stands for ordinary least squares. That's basically the method which Gauss introduced back in the 1850s. Now, we found this matrix here. This is a P by P matrix. This matrix here, and now it's important to keep track of the dimensionalities. This is an N times P, and what you have here is also a P times N matrix. Y has dimensionality N, and this has also dimensionality N. But we can write this in a more compact way, and what comes in now is an important aspect. If you look at this matrix, 1 divided by V, sigma T times sigma of VT, it seems as if we can't do anything, right? Now comes a hidden gem in linear algebra. And the thing, this hidden gem, so this is from linear algebra, if A and B are square invertible matrices, and this is the case of what we have here. So V is a square matrix composed of orthogonal vectors. That is a matrix you can invert. Sigma transpose times sigma is a square matrix, and it has only diagonals, which are non-zero. So this is also invertible. There's no problem with inverting it. So if we do that, then there's a theorem which says that, or a result, which says that A times B is equal to A inverse times B inverse. So that is a property we are going to use now, because I can write then this matrix here as the matrix B, and I can simply say, since this is just a diagonal multiplied with this matrix, and they have the same dimensionalities, then I can define that as a new matrix A. And then I can invert it. And then you will see then, when I invert it, I'm going to get the inverse of V multiplied with that one, and that gives me identity matrix. I have the inverse of this one, which we have here, multiplied with that one, which gives me also the identity matrix. Now, the thing you have to be a little bit careful with now are the dimensionalities, because when I now perform the multiplications here, this guy here has only non-zero matrix elements. But when I multiply, I'm going to have matrix elements here and here, so that one times that one, which can have zeros. But when you perform the multiplication, you get rid of the zeros. So the final result, and try this with just this example we had with a 3 by 2 matrix. So the final result then, what you get when you perform this is actually that Y tilde is given as a sum from J equals 0 up to P minus 1, only for those cases where the singular values are non-zero. So try this out just with some simple examples to convince yourself. And then you have UI, so this is J, of J transposed multiplied with Y. If the matrix is not singular, X transpose times X, if XTX not singular, or as we said, an orthogonal matrix. So let me just, if we can invert the matrix X transpose times X, and we have singular values. So if all, this is all sigma i's larger than 0, then what you would have then would be that Y tilde would be equal to J equals 0 of N minus 1 of Uj of tau of Y. And this would just be the identity. So that means that Y tilde in that case is equal to Y. So what we have done now is actually we have performed a projection where we have reduced the dimensionality of the problem to only include the singular values. And that's a very powerful statement. This has important consequences when we now move to the next method, because then we can make an interpretation of what actually goes on. So this is another way to interpret the ordinary least squares, as you, having performed the singular value decomposition, you have a set of orthogonal vectors, and you use these vectors which correspond to singular values which are non-zero, and you can project out a component of y. So you remember in the previous case, if x transpose times x was given by the identity matrix, then y tilde was equal to y. Now, the question is, why? Why is this interesting? So what we're going to introduce now is the next method, which we're also going to program. So our next method. And that is called ridge regression. So to motivate that one, we are going to do some archaeology. So that means we are going to go back in the 60s, 70s. And one way to deal with this singularity, which we have with the matrix x transpose times x, was simply to add a constant shift. So this is a trick which was introduced, has been used in many, many cases. Trick in case you cannot invert. Invert x transpose times x. So that means that you simply take the matrix x and you change it. So you keep the same matrix plus a lambda times the identity matrix. So you just add a shift along the diagonal. And that normally does the job. If you do that, then you know that the quantity you want to calculate, this quantity beta, and now I'm going to put in ridge here, is actually equal to a new matrix, x transpose times x plus lambda multiplied with this one, and this has dimensionality p times p minus 1 times x transposed times y. You will be surprised to see how often such a trick has been used in many numerical algorithms, simply just to avoid round-off errors or similar things. And this was just a cheap trick. Clearly, you would have to let lambda go to 0 at the end. Now, we can actually get a deeper way of looking at this specific method from an optimization point of view. And later you will see this coming from a statistical point of view, where we're going to use Bayes' theorem. So what you can assume now, so this is just a cheap trick, right? I just add a non-zero positive number along the diagonal. So normally this lambda was put to be larger than 0. Okay? There's nothing wrong with it, not solving the same problem. However, what we can do now is to introduce another function. So another cost function. Which I'm going to call for C for ridge, and I will come back to why it's called ridge, which is just given by the mean squared error as before. So this is the quantity we used till now. And then we have a y of I minus, and if we're doing this polynomial fit, we would have, as an example again, we have this beta j of xi to the power of j squared. But now we introduce a new parameter where we have this lambda And then we simply sum from j equals 0 up to p minus 1 of beta j squared. If I optimize this function with respect to beta, I'm going to get the same problem to invert as this simple trick gave me. And we will see that when we take derivatives now. So this is just another optimization problem. This is another cost function. And this parameter, which you see here, is now called a hyperparameter. And this becomes suddenly a parameter at our disposal, which we can normally tune. So it's pretty common, and you will see later why, to actually put a constraint on the values of beta. This is actually something we will come back to why. So we would typically have a constraint in the solutions that p minus beta, beta j, is less than a number t, which is smaller than infinity. This is simply because if this sum blows up, the optimization part will just be dominated by the term with lambda. So we don't want that term to blow up, because that is going to give us will often give us bad results. But the thing now is that we have this lambda as an additional parameter we can use in the optimization. And you will see that machine learning deals actually with you setting up many such different cost functions. And you're not limited to that form of this hyperparameter term. You can take the absolute value of this beta. If you take the absolute value, then you have something which is called lasso regression. And we will discuss the mathematics of these methods in more detail next week. But these are important methods in linear regression, which also give you more flexibility, in particular, if you have functions where the data are not given by standard or data which are not easily parameterized by a polynomial. So one thing you will notice as well is that if you have a polynomial which you feed in as your data, then normally ordinary least squares is going to beat these methods. So this is one of these other methods which we are going to meet. There is another one which is called lasso, and I'm coming back to that next week. I never remember what the acronym is. I always have to look it up. So this is a sum of I equals 0 up to n minus 1. And then we have the same y of I minus sum over j, p minus 1. And then I have my beta j of xi to the power of j squared. But now I have a new term. And this term is now a term which runs over the absolute values . So the ridge regression is normally called a norm 2 optimization because we have the function squared, whereas this is called a norm 1 optimization. And you will often see this quantity here written out in a more compact way, like a lambda multiplied with beta, and you will see a 1 here. So that's a norm 1. And that means that you're calculating the the absolute values, whereas the previous one is actually given by a norm 2, because you have the function square, beta square. So if we now take the derivatives and repeat the exercises, but now we take this C ridge with respect to beta, and this is us going back to the expressions which you see here, this one. So instead of just taking the derivative of that one, we are now also taking the derivative of this quantity. And that gives us the following. So we want this to be 0. So that gives us minus 2 divided by n. And then we have, as before, this is just the mean square error. And then I have minus, and this comes with minus 2 times lambda times beta, the vector. So these are vectors. When you don't see subscripts, these are always vectors or matrices. And now we can just reshuffle. I multiply away 2 over n from the equations. I want this to be 0. And if I multiply away 2 over n, what I simply get then is minus x transpose or y minus x times beta. And then I have minus, and now I have n times lambda times beta. And I just redefine this as lambda tilde, which I then relabel as lambda. Okay? This is just a parameter, right? So you're free to call the parameter what you want. So if I do that, what you will find is that beta ridge is actually equal to x transpose times x plus, and now I have this lambda times the identity matrix of dimensionality. This is a P times P matrix multiplied with x transpose times y. And this is exactly what we would have gotten if we just cheated with ordinary least squares and we just added a diagonal constant. So you can view this in different ways, but the nice one is actually to think of a new optimization problem where lambda becomes a parameter. And typically what you're going to do now is to run calculation with different values of lambda, and hopefully that will give you a better mean squared error at the end. But it's not given. So you would have to play around with it so it becomes a parameter in your theory. When we are running calculations with neural networks, this would be a typical parameter you would include, this lambda parameter. And that will be part of your full optimization problem. And these are called hyperparameters in the literature. Now, lasso regression, since it has a derivative of an absolute value, will not give you a nice analytical expression. And it has to be solved numerically. Because you have, when you take the derivative of an absolute value, so just to remind you of that, so ridge regression gives us a nice expression. So a lasso, on the other hand, involves the derivative of beta with respect to beta. And that gives a discontinuity around 0. So it will be +1 for beta larger than 0 and -1 for beta less than 0. Now, the kind of trick again, which is being used is to look at the discontinuity which you have at 0 and just put it to 0. But you do have a discontinuity here. So sometimes we cheat a little bit numerically, but here with lasso, you won't get a nice analytical expression, except for some simpler cases, which we will discuss next week. Now, everything we have here can also be derived from a statistical point of view. And we will come back to that next week, because you can also get a deeper understanding of these methods from that point of view. So what we did now was simply to assume that we have a new optimization function, a new so-called cost function, which introduces a new parameter. And this is fully possible. You will find in the literature, if somebody here has studied Lagrangian formalism, does anyone remember that from multivariable, where you could use Lagrange equations to find that the minimal distance between 2 points is obviously a straight line. So you can use actually Lagrangian calculus to show that. So these kind of functions are functions you can think of in terms of a Lagrangian. So you introduce a function with some properties plus some parameters you can adjust. And machine learning deals a lot about finding the appropriate parameters you want to adjust. Sometimes you have no idea and you just try different functions. So in a certain sense, that's the beauty of machine learning, and also the frustrations, because you don't always know exactly what you should do. And then you just try many, many things. And then you pick the one which gives the best result. And sometimes you will find in the literature people saying that we know that that method is supposed to work better, but the simple approach gave us the best results and we stick to that, but we don't know why. You will find results like that. So the mathematics of deep learning, for instance, is a field in great development. Now, I'm going to repeat that exercise now, which I did with ordinary least squares, so that we can understand what is going on mathematically for next week with ridge regression. So what we have now is y tilde ridge. This is the model we have made, which is actually given by, sorry, not that one, but it contains now x multiplied with x transpose times x plus lambda times the identity matrix inverse x transpose times y. Now I can use the singular value decomposition again. And I'm just going to give you the final result, because now I can introduce the singular value decomposition. So that means I can rewrite this one as a u times sigma v of t. I can do the same here and the same here. And then the final result you will get is this one. So you get a sum over the singular values, where you have sigma j squared divided by sigma j squared plus lambda. And this is multiplied with the old vector y. And sorry, I'm missing two things here. I was a little bit too quick. So we are having u of j, of uj transposed, and this is multiplied with y. So in the previous case, when we had ordinary least squares, we had just one here. Now, what happens now is that depending on the value of lambda, we can actually get rid of degrees of freedom. And you will see that. So if you now look at this sigma j's here, they correspond to a specific feature which you have. It could be one of the constants, beta. But if you now think back that this sigma i's, or sigma j, sigma 0, is larger than sigma 1, etc., you can have values here up to p minus 1, which can be very small. If lambda is large then, and sigma is small, then you will suppress a contribution from a component p. So this is a way to suppress. So just keep this in mind, this expression here, and this is the last thing we're going to say today. If you now look at this with sigma j small and lambda large, we can suppress or reduce, is perhaps better, use the role of a specific feature. A specific component u of j. So tuning this parameter lambda, as we will see next week in practical calculations, is a way to reduce the number of degrees of freedom. And this is used in many machine learning techniques. So that means that we can reduce, so this leads to a reduction of the degrees of freedom. So remember that this p corresponds to the number of features you have. So if I fit a 30-degree polynomial, what I can effectively do now with this lambda is to screen away some of these polynomial degrees of freedom. So if I have a 30-order polynomial, I can then, by tuning this parameter lambda, get rid of some of them. And then I can try to which are the most interesting degrees of freedom when I fit a polynomial. Because these J values, which you see here, these subscripts, they correspond to a specific degree of freedom which we have, represented by, in our case, the feature of a polynomial. So we can, by increasing lambda, we can then effectively reduce some of these degrees of freedom. And then we can see which one are the most important ones for making the fit. This is a technique which is widely used in machine learning, because we can have so many degrees of freedom that at the end, we don't see the wood for the trees. And then we want to understand which one can we screen away. So this parameter lambda becomes like a screening parameter. But it is a parameter in the theory which you use to optimize a problem. It may not give you a better result than ordinary least squares, but in many cases where the matrix X transpose times X is not invertible or has strong dependencies, often these methods give better results than ordinary least squares. But this is something which you have to try. And project 1, the first project, deals with you playing around with different ways of optimizing a function. Questions, guys? I hope you were not intimidated by too much of this mathematics, yeah? Yeah. Why do we have to? So the inverting the matrix is just one thing. What you do with this lambda is effectively to screen away some degrees of freedom, which you don't know beforehand. Yeah, that's correct. That's correct. That's a good way to see it. Yeah, yeah.
If a lambda screens away some of the parameters, can you rerun with a smaller p and get better results?
Exactly. So that would be, so one thing, this is a very important question. I don't know if everybody heard the questions. If you now screen away some lambdas and your mean squared error doesn't change much, then you could actually rerun the fit with a smaller set of polynomial degrees of freedom. So this is the kind of way you would actually approach the problem. Now, one thing which we often try to do that is to try to understand when we start to overfit. So this question is very much linked with overfitting, because if we overfit a problem, it means that we can fit to perfection some data, but then it fails on data which was not included in the fit. And then we will see big variations from one degree of freedom to the other one. So this is something we will come back to. That's a very good question. Any more questions? Okay, so then we have the lab sessions, and hopefully everybody has watched this material before the lab. If you're like me, I never watched the material. Okay, but take a look at the material before we meet at the lab session. Okay, see you guys.